The universe operates according to rules we thought were unbreakable. Gravity pulls objects together, light travels at a constant speed, time flows forward. These aren't just theories anymore. They're the foundation of everything we know about reality itself. But what happens when data from one of our most sophisticated telescopes starts suggesting that maybe, just maybe, we've been wrong about some of the most fundamental aspects of existence? The Atlas system wasn't designed to revolutionize physics. It was built to protect us from asteroids. Yet somehow, in the process of scanning the skies for killer rocks, it stumbled upon patterns that make theoretical physicists uncomfortable in ways they rarely admit publicly. Numbers that don't fit, measurements that contradict predictions, observations that challenge century-old equations written by the greatest minds in human history. This isn't about a single anomaly that can be explained away. This is about a systematic pattern of data that keeps accumulating month after month, observation after observation, quietly building a case that our understanding of the cosmos might need a complete rewrite. When telescopes start contradicting Einstein. The asteroid terrestrial impact. Last Alert System sits across two locations, one in Hawaii and one in Chile, scanning the entire visible sky every night. 4 nights out of every month, these robotic telescopes capture images of everything above them, cataloging stars, galaxies, asteroids, and anything else that happens to pass through their field of view. The primary mission is simple enough: find space rocks that might threaten Earth before they get too close. Alert the world with enough time to mount a response. Save civilization from the fate of the dinosaurs. It's a noble goal, one that politicians understand and taxpayers support without complaint. But astronomical data has this peculiar quality. Once you've gathered it for one purpose, it becomes available for countless others. Those same images, meant to track dangerous asteroids, also capture distant supernovae, variable stars, and the faint signatures of galaxies billions of light years away. In recent years, researchers analyzing ATLAS data for entirely different purposes began noticing something strange in the measurements of distant cosmic events. The numbers weren't matching predictions based on our current cosmological models, not by a little, by amounts that suggested either the instruments were systematically wrong or something fundamental about our understanding of the universe's expansion needed reconsideration. The expansion rate of the universe, measured by something called the Hubble constant, has become one of the most controversial topics in modern cosmology. When scientists measure this rate using observations of the early universe, they get one number. When they measure it using observations of relatively nearby supernovae and other cosmic distance markers, they get a completely different number. This discrepancy, known somewhat informally as the Hubble tension, has grown from a minor curiosity into a full-blown crisis that threatens to undermine confidence in the standard model of cosmology. Atlas data has made this tension worse, not better. The survey's ability to detect and measure supernovae with unprecedented precision across vast stretches of the universe has provided some of the most accurate distance measurements ever obtained. These measurements consistently support the higher value for the Hubble constant, the one that disagrees with predictions based on the early universe. Every time researchers hope that improved data will resolve the tension, ATLAS delivers numbers that instead deepen the mystery. The universe appears to be expanding faster than it should be, according to our best theories about how it evolved from the Big Bang. What makes this particularly unsettling is the quality of the data. These aren't fuzzy observations from barely visible objects at the edge of detection limits. Atlas captures clear, repeated measurements of well-understood phenomena. The supernovae it observes follow predictable patterns. Their light curves match theoretical expectations. Everything about these observations should be reliable, yet they paint a picture of a universe that doesn't quite behave according to the rules we've spent decades refining. Some physicists have started suggesting that the problem might not be with our measurements, but with our fundamental assumptions. Perhaps the early universe behaved differently than we thought. Maybe dark energy, the mysterious force driving cosmic expansion, has changed its strength over time. Or possibly, the laws of physics themselves operate differently at cosmic scales than they do in laboratories here on Earth. Each of these possibilities would require rewriting significant portions of modern physics textbooks. Each would represent a paradigm shift, comparable to the revolution Einstein sparked when he introduced relativity more than a century ago, the shadows that move faster than light. Deep space is supposed to be empty, not completely empty, of course. There's always thin gas, stray particles, the occasional wandering asteroid. But between the stars, between the galaxies, space approaches something resembling true emptiness. That makes it all the more strange when Atlas started detecting transient events, brief flashes of light, in regions where nothing should exist to produce them. These aren't supernovae. They're not gamma ray bursts. They don't match the signature of any known astronomical phenomenon. They simply appear, brighten over the course of hours or days, then fade back into darkness, leaving no trace of what caused them. At first, researchers assumed these detections were errors, cosmic rays hitting the detectors, satellites passing through the field of view, software glitches misinterpreting noise as signal. But the events kept appearing in the data, and they displayed patterns that ruled out most mundane explanations. They occurred in the deep space between galaxies, far from any known stars or stellar remnants. Their brightness curves followed consistent shapes, suggesting a real physical process rather than random noise. Most puzzling of all, when astronomers pointed other telescopes at the locations where these flashes had occurred, they found nothing. No galaxy, no star cluster, no visible source that could explain the sudden burst of energy. The distribution of these mysterious transients across the sky adds another layer to the enigma. Rather than appearing randomly scattered, they show a subtle tendency to cluster along certain regions, as if following invisible pathways through space. Some researchers have noted that these preferred directions align roughly with the large-scale structure of the universe, the vast web of galaxy filaments and voids that defines the architecture of cosmic matter. If these flashes are somehow related to that structure, it would suggest a phenomenon operating on scales that dwarf anything we currently understand. One particularly unsettling characteristic emerged when researchers began measuring the velocities implied by how these flashes move across the sky between observations. In several cases, the apparent motion exceeded the speed of light, not by a small margin, by factors of 2, 3, sometimes more. This should be impossible. Einstein's theory of relativity is very clear that nothing can move faster than light through space. The few exceptions known to physics, quantum entanglement, the expansion of space itself, don't apply to these observations. Yet the data persistently shows superluminal motion that can't be easily explained away. The standard explanation for apparent faster-than-light motion involves geometric tricks. When an object moves toward you at nearly the speed of light, projecting material at an angle, you can observe that material appearing to move faster than light across your line of sight. This illusion, called superluminal motion, has been observed in jets from black holes and other extreme cosmic engines. But that explanation requires a source, something producing a relativistic jet. The Atlas transients have no visible source. There's nothing there to produce the effect, nothing that shows up on any wavelength of light humans can detect. The motion appears real, yet impossible, a violation of physics written into high-quality astronomical data. Teams of theoretical physicists have proposed increasingly exotic explanations. Perhaps these flashes represent quantum fluctuations in the fabric of space-time itself, brief moments where virtual particles become real on cosmic scales. Maybe they're signatures of dark matter interactions, the mysterious substance that makes up most of the universe's mass, finally revealing itself through some unknown process. A few brave or reckless souls have even suggested they might be evidence of higher spatial dimensions, brief glimpses into realms of reality that exist beyond our normal three-dimensional experience. None of these ideas have gained mainstream acceptance. All of them require physics far beyond what experiments have confirmed. Yet the data remains, stubbornly refusing to fit into comfortable boxes. When dark energy refuses to sit still, dark energy is supposed to be the simplest part of modern cosmology. It's a property of space itself, a constant pressure that pushes everything apart, driving the accelerating expansion of the universe. The math describing dark energy contains a single number, the cosmological constant, representing the energy density of empty space. This number doesn't change. It doesn't fluctuate. It remains absolutely constant across all of space and all of time. At least that's what the textbooks say. Atlas data suggests the textbooks might be wrong. When researchers use Atlas observations to map the expansion history of the universe, they find hints that dark energy strength may have varied over cosmic time. The evidence isn't overwhelming, not yet, but it's persistent, showing up in multiple independent analyses, refusing to disappear even when scientists apply increasingly sophisticated statistical techniques. The variations are subtle, perhaps a few percent difference between the dark energy density 10 billion years ago and its density today. But even subtle changes would have profound implications for our understanding of fundamental physics. A varying dark energy density would violate one of the most basic assumptions underlying the standard cosmological model. That assumption that the cosmological constant actually is constant comes from theoretical arguments about the nature of space-time itself. If empty space has an intrinsic energy density, that density shouldn't depend on where or when you measure it. Finding variation would mean either our theoretical understanding is incomplete, or dark energy isn't really a property of space itself. Maybe it's a field, something dynamic that can change its strength, like the Higgs field or electromagnetic field. Such a field would require new physics, new particles, new forces of nature we've never detected in any laboratory experiment. The implications extend far beyond abstract theoretical concerns. If dark energy strength has changed over the history of the universe, it will continue changing in the future. The fate of the cosmos depends critically on how dark energy behaves across vast stretches of time. A constant dark energy leads to one future, an eternally expanding universe that grows increasingly cold and empty. A varying dark energy opens up other possibilities. Perhaps the expansion will eventually slow or even reverse. Maybe the universe will recollapse into a big crunch. Or possibly, dark energy will strengthen over time, leading to a big rip scenario where space itself eventually tears apart. Each future depends on details we don't yet understand. Atlas provides the kind of data needed to distinguish between these scenarios, assuming we can make sense of what it's telling us. The survey's ability to detect and measure supernovae at enormous distances allows researchers to map cosmic expansion history with unprecedented precision. Each supernova serves as a cosmic lighthouse, its intrinsic brightness known well enough that measuring how bright it appears tells us how far away it is. By comparing distances to velocities, astronomers can reconstruct how fast the universe was expanding at different points in its history. Those measurements, when plotted carefully, reveal the signature of dark energy's influence over time. The subtle hints of variation in that signature could be statistical flukes, random chance-producing patterns that look meaningful but actually contain no real information. Every researcher analyzing this data acknowledges that possibility. But with each new batch of Atlas observations, the hints grow slightly stronger, the statistical significance edges upward, and the possibility that we're seeing something real becomes harder to dismiss. Eventually, the data will either confirm the variation conclusively or rule it out definitively. Until then, cosmologists find themselves in the uncomfortable position of not knowing whether the foundation of their field needs rebuilding. The asteroids that appear from nowhere, Tracking asteroids requires patience and precision. An asteroid appears as a moving dot in images of the night sky, shifting position slowly from night to night as it orbits the sun. By measuring those positions carefully over extended periods, astronomers can calculate the asteroid's orbital path with remarkable accuracy. This is how we know which asteroids might someday threaten Earth. We track their orbits, project those orbits forward in time, and identify any potential future collisions with our planet. The math is well understood. The predictions are reliable, except when they're not. Atlas has discovered dozens of asteroids that appear without warning, following orbital paths that should have brought them within detection range years earlier. These aren't tiny rocks, barely large enough to register on sensitive instruments. Some measure hundreds of meters across, large enough that previous surveys should have spotted them multiple times before ATLAS finally caught them. The fact that they went undetected for so long makes no sense. Space surveillance has improved dramatically over recent decades. The sky is monitored more thoroughly now than ever before in human history. Objects this size shouldn't be able to hide, yet somehow they did. The orbital characteristics of these late discoveries add to the mystery. Many of them follow paths that bring them unusually close to Earth, closer than would be expected for a randomly selected asteroid from the main belt. It's almost as if these objects are specifically targeting our planet. Though, of course, that interpretation requires intentional direction that natural asteroids don't possess. The statistical clustering of near-Earth encounters among the population of previously undetected asteroids exceeds what chance alone should produce. Either the surveys that preceded Atlas were systematically missing a specific type of orbital configuration, or something about these asteroids makes them inherently difficult to detect despite their size. One proposed explanation involves albedo, the reflectivity of the asteroid's surface. If these objects are unusually dark, absorbing most of the sunlight that hits them rather than reflecting it, they would appear much dimmer than typical asteroids of the same size. Dark asteroids certainly exist. Carbonaceous asteroids can have albedos as low as 3 or 4%, making them extremely difficult to spot even when relatively nearby. But finding so many dark asteroids in near-Earth orbits would itself be surprising, requiring some mechanism to preferentially deliver low albedo objects to Earth-crossing trajectories. Another possibility involves spin states and irregular shapes. If an asteroid tumbles chaotically rather than rotating smoothly, and if its shape is highly elongated or irregular, its brightness can vary dramatically depending on its orientation. At certain angles, such an asteroid might appear much brighter than at others. Previous surveys might have observed these objects during particularly dim phases, when their brightness fell below detection thresholds. Atlas, with its comprehensive sky coverage and repeated observations, would eventually catch them during a brighter phase. This explanation works mathematically, but it requires an unlikely coincidence of multiple factors, all working together to hide asteroids until recently. A third, more speculative idea suggests that some asteroids might spend portions of their orbits in resonant relationships with planets, particularly Jupiter. These resonances could temporarily stabilize certain orbital configurations, keeping asteroids in regions of space that surveys rarely observe. When the resonance breaks down, the asteroid's orbit shifts into a more visible configuration, suddenly appearing in survey data as if from nowhere. The dynamics of such resonances are complex and not fully understood. Whether they could account for the number of late discoveries Atlas has made remains an open question. Whatever the explanation, the practical implications concern planetary defense experts. If large asteroids can remain undetected until they're already in Earth's neighborhood, our catalog of potentially hazardous objects is less complete than anyone hoped. The whole point of surveys like Atlas is to provide decades of warning before a potential impact, time enough to mount a deflection mission if necessary. Late discoveries compress that warning time, potentially leaving humanity with months or years instead of decades to respond to a threat. The Atlas data suggests we're still missing objects, still vulnerable to surprises from space, despite our growing astronomical capabilities. The light that arrives before it leaves. Causality is one of the most fundamental principles in physics. Effects follow causes. Causes precede effects. Light emitted from a source travels outward through space, reaching distant observers after taking time to cross the intervening distance. This ordering of events is not just common sense, it's woven into the mathematical structure of relativity itself. Without causality, without the guarantee that effects cannot precede their causes, physics as we know it collapses into incoherence, which makes it particularly disturbing when Atlas observations appear to violate causality in ways that shouldn't be possible. The phenomenon first appeared in data from supernova observations. Supernovae are the explosive deaths of stars, events so energetic they briefly outshine entire galaxies. These explosions don't happen instantaneously. They develop over time, starting with the collapse of the stellar core, progressing through a shock wave that propagates outward through the star's layers and culminating in the visible brightening that astronomers observe. The entire process takes hours to days, depending on the star's structure. The light from different phases of the explosion carries information about what was happening at different times during the event. When researchers carefully analyzed the timing of light arrival from several supernovae observed by ATLAS, they found something impossible. Light from later phases of the explosion appeared to arrive at Earth before light from earlier phases, not by huge amounts. The timing discrepancies measured in minutes or hours, not days or weeks, but any violation of causality, no matter how small, represents a fundamental breakdown of how we think reality works. If light from tomorrow can arrive today, then the entire framework of cause and effect becomes meaningless. The obvious explanation would be measurement errors, perhaps the brightness variations interpreted as phases of the supernova explosion actually represented something else, interference from surrounding material, or instrumental artifacts that mimicked temporal evolution. Researchers checked for these possibilities exhaustively. They compared ATLAS data to observations from other telescopes, confirmed the timing against atomic clocks, ruled out potential sources of systematic error. The temporal anomalies persisted in the data, showing up consistently across multiple independent supernovae observed under different conditions. Another potential explanation involves the propagation of light through space. Perhaps the light from early and late phases of the explosion traveled through regions with slightly different properties, causing differential delays that made it seem like later light arrived first. Space isn't perfectly empty. It contains thin gas, magnetic fields, gravitational perturbations from dark matter. These could theoretically affect light propagation in subtle ways, but the required effects would need to be extraordinarily finely tuned, operating differently on light emitted just hours apart from the same source. No known physical mechanism can produce such precise differential delays. The most exotic explanation invokes quantum effects in spacetime itself. At the tiniest scales, far smaller than any particle or wave we can directly observe, space and time might not be smooth and continuous. They might have structure, granularity, quantum foam where the normal rules of causality break down or become probabilistic rather than absolute. If these quantum fluctuations in space-time can occasionally affect the propagation of light across cosmic distances, they might produce exactly the kind of temporal anomalies Atlas has detected. This explanation requires taking quantum gravity seriously at energy scales we've never been able to probe experimentally. It's speculative in the extreme. But it's also one of the few ideas that can account for the observations without completely abandoning fundamental physics. Whether the causality violations are real or merely apparent, their existence in high-quality observational data forces uncomfortable questions. Either our measurements have systematic errors we haven't identified, suggesting our observational techniques are less reliable than we believed, or the universe occasionally permits violations of causality, suggesting our theoretical understanding is incomplete in profound ways. Neither option provides comfort to scientists who depend on the reliability of both measurement and theory. when galaxies forget their history. Galaxies are supposed to tell stories. Written into their structure, their motion, their stellar populations is the history of how they formed and evolved over billions of years. A spiral galaxy's graceful arms trace the paths where density waves trigger star formation. An elliptical galaxy's smooth, featureless appearance records a violent past of collisions and mergers that scrambled its contents. By studying galaxies in detail, astronomers reconstruct cosmic history, piecing together how structure emerged from the smooth early universe to create the rich tapestry of forms we see today. Atlas data includes observations of thousands of galaxies, captured as background objects in images primarily intended to track asteroids and other moving targets. These galaxy observations aren't as detailed as what you'd get from dedicated deep sky surveys, but they're numerous enough and consistent enough to enable statistical studies of galaxy properties across large volumes of space. When researchers started analyzing these galaxy populations, they found distributions that didn't match predictions from simulations of cosmic structure formation. The problem centers on galaxy masses and star formation rates. Simulations predict that galaxies of certain masses should be forming stars at specific rates, with variation around average values, but still following predictable statistical patterns. The ATLAS data shows broader variation than predicted, with more galaxies forming stars either much faster or much slower than they should according to their masses. This excess scatter suggests that something about galaxy evolution is more chaotic, more sensitive to local conditions than current models capture. Even more puzzling are the galaxies that appear too mature for their ages. When light from a distant galaxy reaches Earth, we see that galaxy as it was billions of years ago, when the light began its journey. The farther away the galaxy, the farther back in time we're looking. Young galaxies, observed as they appeared soon after the Big Bang, should show signs of their youth. They should contain mostly young stars, have irregular shapes, display active star formation. Many do. But ATLAS has cataloged populations of distant galaxies that look old, containing large numbers of evolved stars, displaying settled structures, showing little ongoing star formation. They look like they've been around for billions of years, but they existed at times when the universe itself was only a few billion years old.